y'all very much for coming, taking the time to come out and do some basic electricity. It's probably something that you say, God, I don't really need that. I know how to do that. I know how to put my meter on. I've been doing it for years and years, and I get that. But I sat on the NAEC test writing committee for a number of years and helped write the exams, and found out that very quickly the one thing that most technicians fail on a NAEC exam is the electrical section. And it's because the theory is not something we typically learn out there in the field. We learn from the guy who learned from the guy who learned from the guy. Is that probably how most of you guys have learned it? Yeah, so we know how to do it, we just don't know why we do some of the things we do. So we're going to try and get through some of that. We're going to get through some of the terms that are being used. So if you do end up taking a NAEC exam at some point in time, you'll understand the terms that they're looking for. Because we interchange some of the terms in our industry, and they're not exactly what the proper terms would be. My name is Rick Kensel. I've been in the industry since the early 70s. I installed my first unit in 1973. Ran my business in South Louisiana for about 25 years, and then went on to work for Linux Industries, and then now for Coburn for the last 10 years. It's been a good good. I've enjoyed what I've got to do. It's you know, at some point in time your body gives up, and you better have your mind ready, because you have to teach it at some point in time. You know, your body just won't handle it anymore. So that's what I'm doing. Those that can do, and those that can't teach, that's me. I can't do it anymore, so I teach it. So here we go. Let's keep it interactive. You have questions, stop me. Don't be afraid to shout out answers. You're going to get some of them wrong. You're going to get some of them right. It's okay. I'm okay with that, because we're all here to learn. Let's get the average age of the guys that are in this industry. How long have you been in here? You've been in here 1 to 5 years in the industry? Yeah. Over 10 years in the industry? Over 15 years? Okay, so less than 15 years. Oh, well, we got a 115 year. Okay, all right, good. Yeah, all right, well, good. Well, that's good. I've been in here since Jesus was a carpenter. I air conditioned his first house, so it was a good gig. Didn't get paid much, but I'm in good with the good big guys. So, all right, let's roll. How does electricity affect you guys? Really, in the industry, how important is electricity in modern society?
Very, very.
Ooh, yes, and it's getting crazier and crazier, isn't it? The high tech. I went into a McDonald's a while back, and shortly after I got there, they said, "Oh, we can't sell you anything because the computers are down." What happened to just collecting money and writing a receipt? You know, that stuff's gone away. The electricity has become more and more and more of a big part. How does the HVAC industry rely on electricity?
You don't run.
It don't run. Is that right? Yeah, it don't run. And has that gotten more complicated over the years as well?
Yeah.
Yeah, we've gone from AC to DC volts and pulse width modulation signals and all kinds of stuff happening now. What's your role in understanding electrical theory and troubleshooting? What is your responsibility?
Don't fry the unit.
Yeah, we're going to fry some units or fry ourselves, right? Yeah. You're in the industry long enough, you know a few people that have died in our industry because of condensers that are not grounded, and then when the compressor, they walk up and just touch that condensing unit, and they drop dead. So we know that happens. It's part of this industry. So please understand, ground is not a part of the main circuit, but it is a safety circuit that we need to pay attention to. Cool. So it goes back to 7th grade science. The atom. It has a nucleus, the protons and the neutrons are in there, and they had these free electrons that were floating around there. Remember that? They had those electrons that were going around the nucleus of the atom. Some of the atoms, where they have a lot of free electrons, can get knocked out of that orbit. And if I had some sort of a pressure to those free electrons, we could get that electron to start moving around and get bumped from atom to atom, and it just starts moving down. Maybe a conductor. Conductors have lots of free electrons, so those electrons get moved when there's a pressure applied. Now, conductors are metals, and they're generally going to be something that's going to be a copper or aluminum. It may be even silver in some case. an insulator is something that does not have a lot of free electrons. So the electrons don't go from one atom to the other if we have a good insulator. Now, I need you to understand that no matter how good the insulator is, there are conditions where I can make that insulator fail. And in this particular case, we had a couple of wires that were leaning up against each other. They started heating up, started going from one conductor through the insulator to the other conductor. Somebody decided that a wire nut would probably be the best way to fix that, and obviously that didn't work out very well either. So how is electricity produced? There's three ways. We can do it with chemicals, we can do it with magnetism, and we can do it with heat. Now, you know these methods because chemicals is batteries. If I had a battery and I can move electrons from one side to the other, that would be a chemical interaction with producing electricity, and that would produce a current flow in one direction only, so that would be DC, direct current in one direction only. Now, magnetism, we can take a rotating coil between some magnetic fields, and when we do that, we can produce a pulsing electricity, and then we call that AC. It's an alternating current. And this is the one that we most generally use around in our industry. We have power generators that are going to produce this from the generators from the utility companies. And then heat. You guys are familiar with this one. If I take two dissimilar wires and tie them together and apply heat at the outside end of that, it'll produce a millivolt current. And that millivolts will be produced by a thermocouple. If you move that heat to the outside edge, that's going to be called the hot junction. The farther you get it towards that edge, the higher the voltage that's going to be produced. So if you do have one of those old standing pilots at some point in time, and you take the thermocouple and you move it in, say trying to heat it up here in the middle, understand you're going to get less millivolts out of it. Slide it towards the end, towards the hot junction, and you will get the most millivolts produced. Fair enough? All right. So let's talk about those terms that we talk about in electricity. Electromotive force, that's voltage. Electromotive force is called potential. Voltage is the measure of EMF, the electromotive force, and the pressure behind the current. If there's no pressure, the free electrons won't go from one atom to the next, to the next, to the next. The symbol for the voltage is the letter E for electromotive force, right? The voltmeter works by reading the difference in two potentials. It can't read just one potential. So it would be from line 1 to line 2, there would be a difference in two potentials. You would get a voltage reading. Line 1 to neutral, red to common. Any one of those are two different potentials. If I read 0 from L1 to L1, does it mean that there's no voltage there?
No.
No, it doesn't. Just because the voltmeter says 0 does not necessarily mean that there's no voltage there. Is that correct?
Correct.
Good. So we want to make sure that we understand that. We have to see two separate potentials, otherwise the voltmeter is not going to say anything at all. Everybody cool with that? Good, good, good. Current. It's intensity. It's the amperage. Current is amperage. It's the flow of those electrons. The symbol for current is the letter I, which stands for intensity, the measurement of current flow in rated amps. In order for the current to flow, there must be a complete path from the source, L1, through the load, and then back to a different potential. These pathways are called circuits. Resistance. Resistance is the opposition to current flow, and we call that ohms. The symbol for resistance is the letter R. You may see the omega symbol as well on your scale. Resistance is the load. It's whatever you're trying to have do work. Electricity usually does just a couple of things. It either produces heat or it produces magnetism. That's basically all they'll do, heat or magnetism. The size and type of the load will determine the current draw. As long as the pathway, the wire is sized correctly, it should be minimal resistance. I should not see any resistance at all, or very small resistance on the wire itself, because if there's resistance there, we're going to start producing one of two things, either heat or magnetism. Is that right? Okay, so we want to have our wire size large enough that it can handle that particular load. And finally, we're down to wattage. Wattage is power. Now, we typically, in this industry, call voltage power. Hey, you got any power on there? Is the power turned on? We typically go that route, but in its true form, wattage is the power, the output, what we produce, what we net out of the end of it. That's what's power. That's wattage. Watt is typically the letter W or P, and its measurement for power. 1 watt is equal to 1 amp driven by 1 volt. Total power consumed by the homeowner is measured in watts. They use the watt meter on the side of their home to get 1,000 watts, and that would be kilowatts. Is that right? 1,000 watts would be a kilowatt. And we can convert wattage into BTUs. 1 watt times 3.413 equals BTUs. Why would I need to know that? Why would I need to convert watts to BTUs?
In case they ask you how much the bill's going to be.
Well, that might be, okay. That very well may be. If I use heat pumps around here? Yeah, okay, you guys use heat pumps.
Never heard of one.
What size heat strip do you put on a 3-ton system?
But 10 kW.
10 kW, right? Because why do we do that? Because that's what we've always done. Is that right? See, that's the deal. See, that's what I'm trying to get you guys back. Why do we always do what we've always done? Because we just never asked the question behind the theory, right? We never got the theory behind that. When a heat pump goes into defrost, how much cooling is taking place in that house if it's a 3-ton? How much cooling is happening in the house on a 3-ton heat pump? 3 tons? Yeah, so that's 36,000 BTUs, is that right? Okay, 36,000 BTUs. So when it goes into defrost, it's producing 36,000 BTUs of cooling in that house. Everybody with me so far? We bring the heat strips on for what reason?
To combat the cooling.
To combat the cooling. Okay, so we said it's 10 kW, is that right? Somebody break out your calculators, because I know you got them on your phones. Calculators, your 10 kW is 10,000 watts, is that right? 10,000 watts times 3.413.
34,130.
34,000 BTUs. So when we're flipped into defrost and we start cooling at 36,000 BTUs during that defrost cycle in the house, we just brought on 10 kW, which is 34,000 BTUs of heat to compensate for that cooling that's taking place right there. Does that make sense?
Now it does.
Now it does. Is that right? When that customer starts calling us now and says something like, oh, I don't know, it's about 2 o'clock in the morning and all starts blowing cold air. And you're looking on that 4-ton unit and you're seeing only 10 kWs coming on. If they got 48,000 BTUs of cooling coming on and you got 34,000 BTUs of heating to compensate, what's it going to feel like in that house when it goes into defrost? Bang. How important is theory? Yeah, I'm with you. I'm with you. I'm with you.
Flip your switch to emergency heat. I'll see you in the morning.
Yeah, you got it? How cool is that? All right. AC and DC, guys, you got a direct current. It's just going to start off at one pole, go straight to the other pole, and then end up. So it's just a direct current. Alternating current, it's going to change direction. It's going to get you 120 volts, down to 120, 120 positive, 120 negative, 120 positive, 120 negative. It's always going to be alternating. Who's gotten shocked in this industry? If you haven't, you haven't put your fingers in there. Right? So when you feel it, you feel that pulse, right? Is that it? You got that? Yeah, you know what I'm talking about. That is the alternating current that you're feeling in there. If you got hit with DC voltage, it'll bite you because you hang on to that. It's gonna cause you to clamp on and hang on. So understand that could be a lot worse. But it's only small voltages, is that right? I mean, a battery's only 12 volts, right? Yeah, what does it do to a screwdriver when you lay that across with a battery terminal?
You got weld it too.
Yeah, you're gonna get another screwdriver. You're gonna bring that one back to Coburn and say, oh, that was defective, right? Yeah, I know how you guys do that. I've seen y'all play that. All right, so understand that it's not the voltage, but it's the current that's going to tear you up. This is Ohm's law. Ohm's law is something some of you guys may have learned back in trade school and said, I'll never use that again. Don't need it, not gonna need it. If I know E is my voltage, I is my current, R is my resistance, E divided by I equals R, E divided by R equals I, or I times R equals E. Easy enough? You follow that? Okay, let's do it again. Watt's law. P is my wattage, E is my voltage, I is my current intensity. P divided by E equals I, P divided by I equals E, and I times E equals P. Everybody good with that so far? All right, so that's how the formulas go. We're going to work with that. All right, so what kind of heat strips do we use? What's the wattage of the heat strips? What do y'all use out there? Give me a 5 kW? 5 kW heat strip. 5 kW is 5,000 watts. Is that right? Good, 5,000 watts. Voltage, let's say 233 volts, because we measured it. What's the amp draw that you're going to have on that heat strip?
21.
About 21, right? Because you know that because that's what we've always done. Is that right? And I'm with you. I'm with you. So 5,000 watts divided by my 233 equals 21.5 amps. Everybody good with that? Cool. Well, what if I found a heat strip in the truck or in the supply room or wherever it is, and I measured the resistance on there? If I measured the resistance and it came out to 11.4 ohms of resistance, and I knew that I might apply 240 volts to that, I can tell you what the amperage is going to be on that heat strip. It'll be 21 amps. If I'm going to get 21 amps at 240 volts, you have any idea what kind of heat strip that might be?
Melted one.
5 kW? It would be a 5 kW heat strip. You just identified that. So let's take it one step further. You said you had multiple sizes. What about, anybody seen a 3.5? 3.5 kW? Yeah, some old ones out there. What's the amp draw supposed to be on that? Ah, see, we're going, yeah. As soon as we get out of our norm, what we see every day, then we go, I don't know. We can do that. Plug it in. 3,500 watts, 3.5 kW, divided by whatever voltage, let's call it 2.333, 233.
15.
Yeah, I'll end up with 15 amps. So when I pull 15 amps, I know that it's doing what it's supposed to do. Is that right? Good to know? Nice to know? Good. I'm with y'all. All right. So how many amps would a 1,000 watt coffee maker and a 1,200 watt microwave pull if they were both plugged in and running at 123 volts? You say, well, I'll never use Ohm's law. But all of a sudden, you might need it in your home. If I had a 1,000 watt coffee maker and 1,200 watt microwave, that's 2,200 watts, is that right? Divided by 123 volts. One more time?
16.8.
2,200 watts divided by 123 volts.
17.8.
17 amps, is that right? 17.8 amps. Is everybody good with that?
Yeah.
If it was on a 15 amp breaker, what's going to start happening? If it's on a 20 amp breaker, what's going to happen? It's okay, is that right?
Mm-hmm.
Be okay on a 20 amp, but it's not going to be okay on a 15, right?
Right.
Is that making sense to you? You guys can use Ohm's law. There's ways that you can utilize Ohm's law. I need you to be able to understand that. A lot of people teach electricity using water faucets and stuff like that. I never got my head around that. So Jody and I spend our life on the road, and we have a lot of windshield time to be thinking about things. So this is one of the things that I came up with, and I wanted to run this past you. If I had a lake 120 feet up the side of a mountain, and I had another lake down at the bottom of that mountain, does this lake have the potential to flow into this lake?
Yes.
It's got the potential to flow there, is that right? Yeah, it's the potential. It is the electromotive force, the voltage that's going to happen. What do I need to have in order for that lake to flow to this one? A path. Okay, so if I dug a little ditch from there to there, I would have, I have a path for that water to flow, is that correct? Water flowing, we call that what? Current. We call water flowing current. Well, isn't that kind of weird? That's exactly what we call our electrons flowing, is current. So that water flowing is the current. That's the amperage as it starts running down there. Now if I threw some big boulders in that river, what would that do to the current?
Resistance.
Resistance. It's the opposition to the current flow, is that right? Good. So if I have these big boulders in there, 6 rocks in that river, that's going to be the opposition to that current flow. So what's going to happen on the other side of those rocks is we're going to start seeing the white water, right? We're going to start seeing the turbulence that's coming up on the other side. And if you are a whitewater rafter and you're standing on the mountain looking down at all that white water down there, you say, man, look how powerful that river is. Is that right? That power is the net result of the current and the resistance. We're going to see that white water. Now, what would happen to that current if I pulled out half of those rocks? If I reduced the resistance by 50%, what's going to happen to the current flow?
Be stronger.
Current flow is going to increase. What do you think is going to happen to that white water on the other side if that current flow increases and we start seeing it hit those rocks now? Reduce? If I have water flowing a lot faster and it's hitting those rocks, what do you think is going to happen?
Increase.
It's going to increase. Absolutely, it will increase. So that white water is going to increase because I reduced the resistance. And let's prove that out with Ohm's law. Ohm's law and Watt's law say this: if I had 120 volts and I had 6 ohms of resistance, my current would be 20 amps. Is everybody good with that?
Yes.
20 amps times my 120 volts will give me 2400 watts. Everybody agree with that so far? We said that current was going to increase and we said wattage was going to increase. Is that right? Good. So, if I reduce my resistance down to 3 ohms, 120 divided by 3, my current just went up to 40 amps. Everybody good with that? 40 amps times my 120 volts, my wattage went up to 4,800 watts. Is everybody good with that? Good. I like this method because now if you decide you're going to take a NATE exam, what's going to end up happening is they're going to ask you a question like, what happens to wattage when current increases? They're going to ask you what's going to happen to wattage when resistance decreases. You can do the Ohm's law if you'd like to do that, but I think this picture in your head really makes it easy for you to be able to identify. Let me ask you this. You've done this before. You've taken 24 volt loads and added them to a transformer. When you start doing that, let's say you're going to put in a gas heater and then you're going to put in a couple of zone dampers on that same transformer. What happens to the current when you start putting in those extra zone dampers? What happens to the current on that transformer? The amperage go up on that transformer?
Down, start more resistant.
You would think, huh? See, that's our thought process, But if we start amping that out, it starts to burn up that transformer for one reason. What? And what is that reason?
It's drawing more in.
It's drawing more amperage, right? So we're drawing more amperage. So we're putting in more loads. And as we're putting in those more loads, we're seeing that the current is starting to go up. Is that right? So what does that tell you? If you know that your current went up as you start adding those loads, what must be happening to your total resistance? It's got to be going down, right? In order for that current to increase, my total resistance must be going down. It's different than what we think. Is that right? Yeah, absolutely it is. So that's why I need to get you guys into this theory so you start understanding what it's really, really doing. Cool. We're going to get to that. So what would happen to current if there was a river with no resistance? If I pulled out all those rocks and maybe made a bend in that river, what's going to happen to my current flow?
Did it increase?
My current flow is going to increase, is that right? What's it going to do to the edge of that river?
Erode it.
It'll erode it out. So as current increases, I might be able to break down that insulator on the side, is that right? Yeah, that's what's happening. That's exactly what's happening. Your current goes so fast that it's going to start breaking down that insulator, that coating on your wires. Is everybody good? Sweet. All right. So guys, I need you to get here at some point in time in the next couple of days. I want you to make sure you have this either at coburns.com. You go to coburns.com and find HVAC info, and you can go there and get all of this information. Or if you go to Coburn's Connect, you can get it off the App Store or Google Play Store. You can get the Coburn's Connect as well. We're going to have a lot of good information for you there, and I want you to be able to access that. It's free. It's because you deal with Coburn's, we want you to have that. So if you go there and you find the HVAC calculators, there's job site sheets, there's tips and charts. Look into the calculators, the interactive calculators. You see a PIE-EIR calculator. So with that, we can do it like this if we choose to do it that route, or just plug in the voltage, the amperage, and it'll give you the ohms, or plug in ohms and amps, and it'll give you the voltage, or plug in volts and ohms, and it'll give you amps. So it's all there for you. We made it easy. The same thing with the PIE, the Watts log calculator. That's there for you as well. So that's 2400 amps, 20 volts, 120. We've got it all there for you. So we can teach you how to do long division, or I can give you the calculator and let you do long division this way. Does that work for you guys? Okay, cool. All right. So if you're going to take an 8 exam, these are the high points I need you to understand so far. Electromotive force is the pressure of the voltage. That's the pressure. That's what makes the current move. Current is the movement of electrons measured in amps. Resistance was the opposition to the current flow of an electrical circuit. All loads, such as motors, elements, have some resistance. Resistance is measured in ohms. Earlier on in the class, Jody was measuring out the resistance on that switch back there, and he said he had 0 ohms on there. So we know that there was no resistance on that circuit. Power was the rate at which the electrons do work, and it's measured in watts. And 1,000 watts is what?
1 kilowatt.
Kilowatt. There you go. Very good. So when we're talking about circuits, we have open circuits, closed circuits, short circuits. Let's talk about what each one of those is. A closed circuit is kind of backwards from what we would think it would be. Closed means it's a door and we can't get through it, but that's not necessarily the case. It's quite opposite. A closed circuit, if you would think of it as a drawbridge, if the drawbridge is closed, you have flow across there. You start from your house, you go across the switch, the closed switch, to work, where you get work done, and then you head back on that path back home, right? Everything just is a circuit. An open circuit would be that drawbridge is open. You go this way, work can't get done, it's just stopped right there, there's no flow across there. So in that particular case, your switch would be open. Is everybody good with that? Good. A short circuit is a path without a load. What happens to current flow with a path without a load?
Goes nowhere.
How fast does current flow when there's no resistance? Fast. Is that right? We don't have any rocks in that river. The current's busting through there. Is that right? Good. And that's where we start breaking down our, we start tripping breakers. Is that right? Because current just did what? It went up. It went up dramatically. Everybody good? Good. So it trips the breaker. Everybody good? All right. So, source voltage. 240 volt circuits. You'll have typically a red and a black wire run from the L1 side of a dual 240 volt circuit. A black hot wire. It might be red or black, and then the second one will be black. It'll go to the L2 side of that, and then you'll get a green copper or a green or copper wire running from the ground. Now remember, the ground is a safety circuit. It's our safety. We need to make sure we understand safety, and it is only used to make sure that we don't have any voltage that's going to hit to us. So it's our safety circuit. 120 volt circuits. You have a black wire that's electrically the hot wire. We call that our hot wire, and it's attached to the low side of the fuse or circuit breaker. The white wire is attached to the neutral terminal bus in the service panel, and then the green or copper wire again is from our ground, and it is for what?
Safety.
Safety, absolutely.
Please look it up.
24 volt circuits. Red is our hot wires run from the transformer secondary side of that transformer, and then we'll have a common wire, and that's going to be like our neutral wire. Is that right? That's our neutral. It's the second potential in our two potentials that we need to measure voltage. So electrical symbols. How'd you guys get here today?
Car.
You drove here, right? You got here. And when you drove here, there were symbols all along the road. I mean, there was that kind of a symbol, right? What did that tell you to do?
Keep going.
Yeah, okay, well then you're with that guy, I got you. All right, so then there's that one, that meant to slow down and kind of eyeball it, right? And then we got these that says slow down and eyeball it and get hit by a train, right? That's those. So we have all of those symbols. The same comes to pass with the schematics. When we're dealing with a schematic, if I'm looking at something like this and it's got that big S on there, I know that that's going to be fuses. I know that because I've studied schematics for a long time and I understand that. That's what I need you guys to start getting better at. Starting to read your schematics and understand those. You see an S in there, that's going to be a fuse. It's typically in an L1 to an L2 type situation. When you see something like this, you know that that's a transformer, right? We're going to have a high voltage coming into the transformer and then a low voltage coming out of the transformer. In what we do, it could be just the opposite in some of the other things that are out there. We could have step-up transformers as well. When you see a solid black wire and it's thick, that's going to be a factory installed high voltage wire. If you see that it's real thick and it's broken up like that, that means that you guys are going to install that wire. It's high voltage and it's field installed. Same thing happens when the wire is thin. That's going to be factory installed low voltage wire. And then again, if it's broken up, it's going to be field installed low voltage wire. When you see a load drawn like this, it's going to be a resistive load. That's going to tell you that it's going to put out heat. It's going to produce heat. That's a heat strip. That's a crankcase heater. You're going to see that. When it's drawn with the points on it, it's going to be heat. When you see it drawn with the loops on it like this, that's going to be an inductive load. That's going to be a magnet of some sort. Does that make sense to you? There might be a contactor coil. It might be a fan relay coil. It may be a coil on a blower motor. Something like that. Something that's going to produce magnetism. So we have resistive loads and inductive loads in there. This is a switch, and it's typically drawn the way that it's going to be with no voltage applied. So this would be a normally open switch. Very good. This is a set of contacts. Again, with no voltage applied, this would be a normally closed set of contacts. Very good. This is a temperature activated switch. Now, If I apply temperature heat to this, it's going to cause it to open up. All right, so this switch might be for rollouts on a gas heater. So it would typically be closed, but as soon as I overheated it, it would open up. Very good. All right. This is a float switch. Float switch has the ball on the bottom of it. Typically going to be in the normally closed position. As soon as the water level increased, it's going to cause it to open up. Good. This is a pressure switch. In this particular case, if pressure is applied to it, it will open up. So this would be a high pressure switch. If the pressure got too high, it would open up. If it was a low pressure switch, it would be drawn down here at the bottom. And when the pressure started dropping off, it would fall open. Does that make sense? Difference between a high pressure and a low pressure switch. Everybody cool with that? Good. All right. Two paths that are connected on a schematic will usually have a dot on there. Two paths that are not connected are going to just cross over. Everybody cool? Good. And one of the most important ones that are out there is the ground. And ground is our safety circuit. All right. And this is a capacitor. Whenever you see this little C right here, that means capacitor. All right. And we'll deal with that. Cool? Everybody got that? Yeah, we said we got all that. We know that. We've been doing that for a long time. Good. Good. All right. When in doubt, look for the legend on the schematic, because every manufacturer likes to put in something a little bit different on their schematics to be able to just throw you off a little bit. So go back to the legend. All right, so let's look at series and parallel circuits. In a series circuits, how many current paths do I have there? How many paths that the current's going to flow from L1 to neutral? Yeah, in a series circuit, there's only one path. So the current's going to be what? The same or different throughout that circuit? It's going to be the same. If it starts out fast here, it's going to end up fast here. Is that right? It's not that it's going to start out fast and slow down and then pick up, because there's only one path. It's going to be one path. It's only going to be one current throughout that entire circuit. All right? So what it's going to do is it's going to share that voltage. Depending on the resistance on each one of those loads on there, it's going to share the voltage. If all three of the resistances are exactly the same, I have 40 volts, 40 volts, 40 volts. 40 plus 40 plus 40, that's 120 volts. Very good. All right. So it's going to share it depending on the resistance of each one of those loads. All right. Well, if one load fails, what happens to them?
They all fail.
Everybody remember anything that was like this? It's a communist plot to be able to make you hate Christmas. I'm telling you, it's one of those things that just happened that way.
Waste
Right?
your money because you end up throwing them all away.
Yeah, you throw them all away. Absolutely. So one load fails, they all fail. Well, it was a very inexpensive way to be able to run those lights. So they were doing that. So if I had a Christmas tree string of lights and they had 120 lights and they were wired in series, how much would each one of those light bulbs receive? 1 volt. Everybody got that? Yeah. So each one of them is going to receive only 1 volt. All right. Well, they're often used for devices. We use series circuits that are often used for devices that are control circuit or safety circuits. So I might have, what kind of switch is this? Pressure switch, and this is a
Low pressure.
low pressure. So this is a high pressure switch, this is a low pressure switch, is that right?
Yes. Good.
Good. So if I put these switches in series with my load, one of them fails, what does it do? Shuts off the voltage to the rest of it, is that right? So we used our switches in series in order to be able to operate our load or keep our load safe. So here's the things you need to know about a series circuit. The current remains the same throughout the series circuit. The voltage will be divided in proportion to the resistance of each load. So what we basically said there is as the resistances change, the voltage drop on each one of those resistors is going to change. Is that right? Good. If any of the series loads fails, if it opens up, all the loads will stop working. Is that right? Good. Total resistance in series will be the sum of the resistances. So each one of those resistances adds up. I keep adding more resistors, they keep adding up on the resistance. What does that do to the current flow if I keep adding more and more resistors?
Slows it down.
Slows it down. The more rocks, right? Remember the rocks. The rocks will help you. The more rocks I have in that river, the current is going to decrease. Is that right? Good. All right. So resistor 1 plus resistor 2 equals resistor total. The sum of the voltage drops across each of the loads will be equal to the source voltage. So what we saw before was 40 plus 40 plus 40 gives us our total 120. Everybody good? All right, let's go into parallel loads. This is more what we see out there in the industry, is that right? We see parallel loads. So, in a parallel load, I can have more than one path. So, this one would see 120 volts, this one would see 120 volts, and this path would see 120 volts. So in parallel, all the loads receive the same source voltage. That's what we see in our units. The condenser fan motor sees 240 volts, the compressor sees 240 volts, the crankcase heater sees 240 volts, yes? Okay. So, in that case, this is what we're looking at, parallel circuits. All loads receive the full line voltage, source voltage. Total amps of the circuit are the sum of the individual amps measured by each branch. Well, wait a second. If this was my crankcase heater, how many amps am I reading on my crankcase heater? How much current is going through this circuit right now? So how many amps am I going to read on that circuit? 0. On my compressor, how many amps would I see on that circuit? 15, okay, 15 amps. What would I see on my fan motor circuit? 2. So if I had 2 here, 15 here, and 0 here, what would I measure on the line coming into that? 17 amps. So my amperages add up in parallel, is that right? I only had 1 amperage in series, but in parallel they add up. Good, all right. Each load operates independently of the other. If one load fails, the others will continue to work. Is that right? Fan motor stops, compressor still run? Till something else take that out, right? The total resistance of all the branches in parallel is less than the smallest branch resistance. And that was the hardest thing for me to get my head around. The total resistance of all branches in parallel is less than the smallest branch resistance. It basically means as I start adding those loads, what happened to the total resistance in parallel? Remember when we started adding those zone dampers? Oh, yeah, when we started adding those zone dampers, my current did what? Went up. So total resistance must have gone down. So the more resistors I put in parallel, the more paths I have for that current to flow, which means the total resistance of that whole deal is less. Yeah, it's kind of crazy for us to get our head around. Yeah, getting our head around that. And that's important that you get that, because as one thing happens and we're starting to say that it's going to be something else. Is that right? We said, oh, my resistance is going to go up when I start putting those in. If current's going up, resistance has to be going down. Everybody good? Sweet. Can we have series parallel circuits? Yes, we can have some of those as well. We don't see too much of that in this industry, but we can have it, where I would have this circuit here for this light, and that could work, and then I could have a couple of lights in this circuit, and then one in this one. That would be the newer Christmas lights maybe, where they'll have a string of them that goes out when one light bulb goes out, but then the rest of them stay on. So that would be a series parallel circuit. Cool? All right. So let's start using our ohm meter here for a second. Never connect your ohm meter to an energized circuit. Okay? That's how good is that? It's in red up there at the top. So we made sure that we're going to make sure that you guys read that. Never connect your ohm meter to an energized circuit, because what's going to happen? You're going to buy a new meter. And not that I would have any problem selling you a new meter, but the same thing as you guys don't have that kind of money to just be throwing around. So don't connect your ohm meter to an energized circuit. Check the windings using an ohm meter. An ohm meter will send DC voltage from the battery that's inside that meter through whatever it is you're trying. What kind of load is this? A resistive load. Is that right? Resistive load is going to produce heat. Good, very good. So this might be a heat strip we're checking. Is that right? So we're going to send voltage through there and then back to the meter. The meter will then measure how much resistance is in that path. And when it does that, maybe it's 3 ohms of resistance. Everybody good with that? Yes. All right. Now, what would happen if my heat strip was open? Yeah, it's going to come out with OL on there. What does that mean, OL?
Open load.
Open load.
Open load, yeah, open load. How many of y'all knew that before you read it right there? Yeah, I got you, all right. So I'm a Cajun boy and I'm dyslexic. I'm not the smartest tack in the box. So I never could figure that one out. So what I came up with was, that's a lot of ohms. Right? I'm dyslexic, right? I'll turn it back. That's a lot of ohms. How much resistance do I have in this circuit right now? I have a lot of resistance. Will current flow through here? If current flows through that means I must have a lot of rocks in that river. Is that right? A lot of rocks in that river. If I have a lot of rocks, I can stop that current from flowing, correct? How many rocks do I have here? A lot of rocks, right? So in my mind, that OL is a lot of ohms. Okay, that's a lot of ohms. Good? All right. So if I had a short circuit, no load inside there, what would I read on my meter now? 0 ohms. So 0 ohms, do I have a path for current to flow?
Yes.
How fast is that current going to flow? No resistance. The path is going to be wide open. It's going to be a huge amount of current. Is that right? That's different from OL, which is a lot of ohms, and you will have no path. Is that right? Good. All right. Good. So, checking using the ohm meter, checking your compressor using your ohm meter, we can identify some stuff. So let's try that. We're going to disconnect the C, the common, the S start, and the R run from the compressor terminals. And this is basically what you're looking at inside there. An ohm reading with a number such as 0.5 ohms or 2.4 ohms states that there's some resistance in that winding. The resistance coil and current flow create the magnetism needed for that motor to turn. Well, common doesn't have a winding. It only has a switch. What kind of switch is this? Thermal switch, a temperature activated switch. So as that temperature starts increasing, it opens up that switch. Is everybody good with that? Good. What I do have is a run winding and a start winding. Run winding and start winding. So let's measure this stuff out. Here's my common, here's my run, here's my start, there's my meter. If I put it on common and I put it on start, I might end up with 1.6 ohms. Everybody good? Good. I'll write that down somewhere over there. If I put it on common and run, I might end up with 6 ohms. Which one's the more resistive? The the run or the start? Which one's more resistive? The start winding is a tighter wound winding. It's real tight and it's going to have a lot more resistance in it than our run winding will. Okay, so it proved that out. So if I go from run to start, it should be the combination of both of those. Is that right? Good. So what you're expecting to see is 1.6 plus 0.6 is 2.2 ohms is what I should be seeing right there. So let's look at that. If I saw that I had 1.6 on my start, 1.6 on my start, 0.6 on my run, I should see the combination of both of those resistances between the run and the start. Everybody cool? Good, good, good. All right, so if it's working well, if everything's ohming out correctly, I should have a ohm reading from common to run. I should have an ohm reading from common to start. The ohm reading from run to start should be the combination of both of those. Yes? Good. And there should be an OL reading from any terminal to the compressor case. Any one of those to the case, I should have a lot of ohms. I should have no path for current to flow from any one of those to the case. So touching there, touching to the case, I should see OL, or a lot of ohms. Everybody good? Sweet. All right. What do we have here? Open what kind of winding? Open start winding. Everybody okay with that? Good. Because what's going to happen is you guys are going to start sending compressors back that are under warranty. And you're going to send them back, and Jody's going to say, yeah, they sent it back and said it was not. What do you typically, when you send in a compressor and something's wrong with that compressor, what would your first instinct be to write down on what's wrong with that compressor?
Grounded.
Oh, grounded or bad, right?
What
It's a
Carl
bad
wants to
compressor.
listen.
Oh, you're a bad compressor. Bad compressor. Bad. Come on. There's no bad compressors. They're either open, they're shorted, they're grounded, there's something. Is that right? Give me that information, because there's somebody at the other end that doesn't have a clue what's going on. But as soon as they get the information that you said it was bad and they don't see bad on their check sheet, what are they going to do? Send it back down. And whose money's tied up that whole time? Yours, okay? So let's get these things, let's get our terminology right on these things. In this particular case, what's wrong with this compressor? Open start winding. We can see it because it's visual. But if I had an open start winding, would I get an ohm reading from common to run?
Yes.
Is there a path?
Yes.
Yep. I'd get an ohm reading. Would I get an OL reading from common to start?
Yes.
Because there's a lot of ohms. Is that right? Good. Would I get an OL reading from run to start?
Yes.
Yes? Would I get an OL reading from any one of those to the case?
Possibly start one.
Good. All right. Let's look at this one. What happened to my thermal overload? It opened up. What would I read from common to start? OL. From common to run? OL. From run to start? I'd get an ohm reading, is that right? Would I get an ohm reading from any one of those to the case?
Is it a Nordine unit?
Would I get an ohm reading from any one of those to the case?
No.
No. It's going to be OL, is that right? Would I ask that question sometimes, what's the ohm reading? You're not going to get any ohm reading. It's not going to be, it's going to be nothing. Well, nothing is zero, is that right? Zero means a path, is that right? So am I going to get an ohm reading? What kind of ohm reading am I going to get? A lot of ohm reading. See, and that's the piece that I know it's simple here, but when we're talking to a young technician and you say, well, there's no ohm reading, there is an ohm reading. It's a huge ohm reading. Does that make sense? It is a huge ohm reading from there to there. Very good. All right. Now what's happened? Now we have something that part of our winding is actually touching that case. So if that happens, I have a grounded compressor. Ohm reading from common to start. Will I have an ohm reading? Is there a path?
Yeah.
Yes.
There is a path, right? So I'm going to get an ohm reading. Is that right? Will I get an ohm reading from common to run? Get an ohm reading there. Will I get an ohm reading from run to start? Yeah, sure will. Will I get an ohm reading from start to the case?
Yes.
Yes. See, and it might be any number of readings that I'm going to get, but it's not going to be OL. Is that right? Cool. In this particular case, we have a grounded compressor. Is that right? Good. It's grounded. What if that entire winding just melted together? It just turned into one big piece, one big chunk of copper. It got so hot it just melted all together. How much resistance would I have if that winding just turned into one big piece of copper? Very little resistance, is that right? Very little resistance in there. So in that particular case, we would have a shorted run winding. The ohm reading from common to start, would I have that?
Yes.
Would I have an ohm reading from common to run? It might be very minimal, but it might be 0 ohms, is that right? Good. Would I get an ohm reading from run to start?
Yes, same thing.
Because I still got resistance here. Would I get an ohm reading from any one of these to the case?
No, no.
I'd get an OL reading on there, is that right? A lot of ohms. Good. All right. So this would be shorted because that's where my... Now, could I have shorted to ground? Yeah, sure could have something like that if it was actually touching the outside case. It would be shorted to ground. But understanding the difference between shorted and grounded is two different things. Cool. All right, here's your break time.